So hi. So in the last video we discussed the main principles of a synchronous machine, and in this lecture we will discuss the equivalent circuit model of a synchronous machine. So it will be similar to what we did with the DC machines. We will approximate our machine with using a equivalent circuit. We will do all our mechanical and electrical calculations using that circuit. Okay, so first let's discuss how the things gets built up in a synchronous machine. So we have some causes, and that things create some voltages and currents. So there's a cause and effect relationship. So everything starts with the field current. So we apply some DC current to the rotor while it is rotating. So it creates a MMF field, magnetomotive force, in the air gap and in the stator windings as well. So that, you know, MMF actually creates some flux. So remember, MMF is equal to flux times reluctance. So that flux, okay, that total flux creates while it's rotating, and we have three-phase windings in the stator. So that thing creates the induced voltages EA, EB, and EC. So if you just leave your machine open circuited, and you can connect the oscilloscope, so there will be no stator currents, but again you will not be producing or utilizing any power. So what we do is, you know, we connect the machine to a circuit. Again, it can be run as a generator or as a motor. It's just a mode of operation. So then you have the currents, okay, but then the interesting thing is that those currents have their own, you know, resistances and inductances as well. So you create some MMF, okay, stator MMF, it's called the armature MMF, and that thing creates the armature flux, okay. That AR is the armature, and armature flux is the flux due to the current in the stator, okay. That is different from the field flux. So then, you know, again in the air gap, they don't know which flux is coming from other one. So there we have a resultant MMF, which is phi r, and it is the addition of field and the armature reactance or armature flux, okay. So, or, you know, again we will derive those things, or you can think the same thing as like the multiply excited system, and they will try to increase their either self-inductances or mutual inductances. But anyway, if you look at the flux vectors, you have something like that. So that is while the motor is rotating, so you have the BF. So this is for, let me write it here, it will go down. This is field. Again, it is B is for the flux density, or you can take the normal flux, okay. Then you have the EA. So this is the let's say open circuit voltage, okay. Then again, let's say I'm talking about the phasor here. So let's say you have a lagging current. It doesn't have to be, but let's assume there's a lagging current here, and due to that current there's some 90 degrees between that current and that flux. We will talk it Y, but then that B, it's not here, but it's just shown in the origin. So that is the flux created by the armature itself, okay. So we induce some voltage, and again there's also on top of that voltage there is some current flowing through the windings, and we have that AR. So at the end of the day, both these things are, you know, flux densities in the air gap, so they add up, and what you end up is the resultant flux, okay. So this is armature reaction, and this is the field flux, okay. So all added up, and I will end up with that one and that flux, okay, and there is some angle in between, okay. So that angle in between is actually are, the distance of the caret between donkey and caret. So actually, again, if they are all aligned and if that angle is 0, then there is no torque generated. They are already at the minimum energy position. Okay, so that is, physically, again, it is physically difficult to measure. I mean, you need to put some Hall effect sensors and that kind of things, but that is how we built our equivalent circuit model. Again, I don't want to get into like really detailed model, detailed derivations, but I will upload some documents to the OT class, so you can have a look at the derivation here. But in short, okay, so that angle, let's call it delta, the load angle. So the force is actually the acting between the resultant and the field flux. So field flux is always trying to catch the resultant flux, okay, and the higher the distance, again, there's some simplification here. We assume a sinusoidal distribution, and we will derive those things as well. But you can think like the torque, again, is proportional to field flux. Again, if there's no field flux, we will not have any torque, and there's some resultant flux, and also the angle between these two, and k is some constant. Again, we will discuss what it is in the following lectures. But now the important thing is the load angle, and we will be using all along the equivalent circuit. So load angle is the angle, physically, unfortunately you will not be able to make the experiments this semester, but there were a way of seeing that in an actual machine. So if that angle is larger, then you generate more torque. If that angle is 0, then you don't generate any torque. So it's already aligned into the minimum energy position. The delta is larger than 0. We will use it in the phasor diagrams as well. So that is operating in the generating action, or you can think as if the rotor, okay, the rotor is moving ahead of the stator. So the rotor is pulling the stator, so it is transferring power in that direction. So it is the generating action. Or if delta is less than 0, again, it is as if you can think like you are applying some power through the electric supply, and your MMF is moving forward, okay, and then rotor is lagging behind, and you are pulling rotor to do some mechanical work. Okay, those things all will be clear with phasor diagrams and power flow diagrams, so don't worry if you are confused now. But the important thing is you can generate maximum torque at plus or minus pi over 2 at 90 degrees. That is the maximum torque point. And again, this is not the actual mechanical angle. Here we are talking about the electrical angle. Okay, and again, another important part is if there is no phase difference between these two fluxes, okay, so when load angle is 0, so you don't generate any power or you don't generate any torque. So that is the case where you already has the minimum reluctance or whatever minimum energy point, or the point where donkey eats the carrot. Okay, so the waveform is like that. Again, don't worry about the direction, how to define positive and negatives, but it is, you can think like it's a spring. Okay, if you are pulling in the one direction, so the flux starts increasing and increasing, and you reach to the maximum torque value. Okay, so this is T max. Okay, and if it is pulling in one direction, for example, if your electrical system is lagging behind, or if you are applying some mechanical power to the rotor, and that is generating the voltages, so that is operating in the generator mode. Or if it is the opposite direction, again at minus 90 degrees, I have minus, let's say, T max. If it is linear system, they are symmetrical. And in this case, again, maybe you can think of the donkey and carrot analogy. So here the carrot, okay, the carrot is actually our mechanical system. Sorry, the donkey is our mechanical system, and the electrical system is moving ahead of our mechanical system. So electrical system is running away and actually is pulling the mechanical system. Okay, we will define all those things. So let's talk about the phasor diagram. And normally the induced voltages lags the armature flux by 90 degrees. Okay, so, or actually let's define why we have that 90 degrees, or why the induced voltage lags our flux by 90 degrees. And again, remember, our flux is proportional with our armature current. Actually, it can be any induced voltage in an inductor. Okay, so let me pull out it here. Okay, so you can have the current which is proportional to flux, and then you can have the voltage in that inductor. So why the voltage, the induced voltage in an inductor, lags the current by 90 degrees? Again, you can think it as like the cause and effect. So the cause here is the current, so you're applying some current, and that will create some voltage, and the effect actually follows the cause by 90 degrees. Anyway, let's define it mathematically. Okay, I can write here like any, if you remember, induced voltage in a coil, it was what? Minus n d phi over dt, right? This was minus d phi over dt. Or in other words, if you, let's say, phi is in the form of sine something, okay, then EA will be in the form of sine derivative. There's another minus, and minus cosine something, right? And if you plot those things in real, actually you will see they are lagging behind. But why we have that minus? Okay, so actually if you think of the phasors or the complex domain, so what we have, if you plot those things, let me draw it nicely. Okay, let's say you have that thing, and I have let's say this is my, okay, that is my flux, which is proportional to current, and that statement says, okay, that statement says actually EA, or if you are, let's use a smaller caption here, so it is lagging behind by 90 degrees. Actually you can define the same thing. So here it is j omega, it goes like that, right? So actually I don't like the definition where, like in maybe second year, you have seen like complex number is like j is equal to square root of -1. What I like is g plus j is equal to -1, right? So that means if you apply j, that right here, apply j is equal to 9, rotate 90 degrees. Okay, so if you apply j once, you get 90 degrees rotation, and apply again and you get like 180 rotation is equal to j square, that is equal to -1. Okay, so again, if you are not familiar with phasors, I think it's good to understand why it is lagging, why there's a minus here, which is the cause, which is the effect kind of relations. Anyway, at the end of day, okay, at the end of day, armature reaction can be represented as a voltage drop in an inductance, because actually that is what it is, because you have some flux. So by definition, inductance is equal to flux created per current, flux linkage created by some current, and there is some j omega L relation or 90 degrees phase difference between voltage of an inductance and current of an inductance. Okay, so it is something like that. But on top of that, okay, so again this was just the armature reactance, and the resultant is like EF, the field flux, minus the armature reactance. Again, don't worry about the plus or minus, they're all conventions. Okay, so let's add up all those things. Okay, and we assume, that is important, we assume a cylindrical rotor. Okay, constant air gap distribution. So in other words, no reluctance torque for now. Okay, for the simplification, we will not have the reluctance component. We will add those things we will use a different equivalent model for salient pole synchronous machines. But for that one, this is a cylindrical rotor and there is no reluctance torque component. Okay, so then everything can be written like that. So the idea is, let's go step by step. If you don't draw any current, IA will be 0, and the back EMF or the phase voltages will be equal to induced voltage due to just rotation of the rotor. Okay, so you are rotating rotor is generating a three-phase voltage. So again, that will be your voltage. But if you draw some current, it can be either in that direction or in the opposite direction, but again it is AC current, but we have some conventions which I will explain shortly. Okay, there will be some voltage drop on top of those armature windings. So these are shown with a inductor, and that inductor will be there. And on top of that, there's also, if you remember the equivalent transformer model, there's also the leakage flux. So leakage flux, you can think of the self-inductance of the coil, which doesn't link the secondary coil. In our case, it is the other windings or the rotor flux. Okay, so we can define the stator total reactance as the JXQ, JXL. Okay, so at the end of the day, I will be using that one. Okay, so this is the stator total reactance. So that will be used in our equivalent model, and it will be something like that. So there's some terminal voltage here. Okay, and I will have EF is the no circuit, open circuit voltage, and there will be some current flowing in that direction, and there's some voltage drop in that series inductance. And again, on top of that, we will have the resistance of the phase windings. Okay, so there will be some voltage drop in that resistance. So you can write that one, include that one as the armature resistance here. Okay, so with that one, so the phase voltage, okay, or terminal voltage is equal to EF minus JX plus RA. Okay, there's no J component, it's directly proportional to current, multiplied with the current phasor, current vector. Okay, again, this is the convention. If a synchronous machine can operate either as a generator or as a motor. Okay, and we use this convention, okay, just to show the power flow. If it is motoring, I will use as if the current is getting into the machine, or if it is working as a generator, I will use the convention showing as if the current is going out of the generator, but at the end of the day, remember, all that current is AC, so it's just coming in and out, so there's not positive direction or negative direction. But I will use that conventions to define where is my zero angle in those phasor diagrams. And I will show a couple of examples under different conditions, so I hope that will be all clear for you. Okay, so again, that's equivalent circuit, that is per phase equivalent circuit. Okay, that is important, that is per phase equivalent. But in reality, okay, actually synchronous machines are, you know, three-phase machines. Actually there can be in 5, 7 or whatever phase machines, but the most commons are the three-phase machines. And those three-phase machines, as I showed in the previous videos, they are connected either Y or delta. So you have a common point and you will have the terminal voltages getting out. Okay, so the important thing is you can make all your calculations in single phase or per phase equivalent circuit like we did with the transformers. Okay, but while calculating the total power, I don't know, total line to line voltage or torque, whatever, don't forget to, you know, multiply it by 3 or square root 3. Okay, so you need to be aware of the calculations that we are doing is just for one phase of the system, or it's just per phase of the system. Okay, again here you see an example of the delta connection. So again here, like per phase voltage is equal to line voltage, but the currents are, you know, added up. Again, it doesn't make like 2 times IA. Don't forget, it's all AC system, so the line current will be square root 3 times of the phase currents. Okay, so there are two very important definitions to remember. We'll show those phasors in the next slides. The first one is the load angle. Okay, load angle is either physically, you can say, the angle between the rotor field flux and the stator flux, or that is equal to the induced voltage, phasor in the induced voltage, and the terminal voltage, that is the load angle, because that defines which direction is the torque generated or which direction does the power flow. And secondly, again, you are familiar with that one, power factor angle, theta. So that is the angle between the phase voltage, okay, at the terminal side, terminal voltage, and current. Okay, so let's ignore, okay, just for simplification we will use the full circuit, but for now just neglect RA. So as if the machine is 100% efficient, there is no resistance voltage drop in the stator windings or something like that. So here, okay, that is the simplest model that you can have. Let me get rid of myself. So here you have the induced voltage, EF. Okay, it is either shown by E or EF. Okay, so here again, if, I mean, it is not important, okay, it is not important how do you put the phasors, where is your zero angle. Okay, you can put everything, okay, you can put everything rotated. You can take EF as the zero angle and you can draw everything with respect to that EF, or I mean the more common one is to take the terminal voltage, okay, this is the terminal voltage, as zero voltage. This is the induced voltage. But the important thing is the angles between them. Okay, so if again I'm assuming assumption here, we cannot just know, let's say I is lagging. Okay, if I is lagging, if this is my voltage, okay, and this is my current, so this is my power factor. Okay, so this is my power factor. Okay, it's operating, again it just shows it is operating as a generator. Again, the convention, it is the power as if it is flowing out of the generator. And how do I plot the voltage drop in that one? It is JXS times I. So that means, okay, so you have that I vector, okay, that I vector is here, okay, multiplying by J, remember, multiplying by J, I just showed in the phasors, it is rotating 90 degrees. Okay, you are taking the derivative. If it is sine, it's becoming cosine. So you have the I vector like that, it is lagging behind the voltage, and you are multiplying by Jx, so you are taking the voltage drop here, so it becomes a 90 degrees phasor like that. So it is J times I XS. Okay, so that is the voltage drop here. Then you add that voltage plus the voltage drop on the inductor, and you come to that point, and that is where you have the E. Okay, and the angle, okay, the angle between voltage and current is the load angle. Okay, so this is the power factor angle, so this is the load angle, and we will, the usual convention is like the rotation is like that. So in this case again E is ahead of terminal voltage, so it is as if our E, or like rotor, is pulling the electrical system. So you can again see it from here, the power flow is like that, or it is working in the generating mode of operation. Okay, so let's do a couple of exercises with the simple equivalent circuit, and I hope it will be all clear. Okay, so again let's start the same thing, but I will change the magnitudes. Let's say again for this example IA is lagging, okay, and generating mode. Anyway, let's plot the same graphs again, right? So let's say this is our terminal voltage, right? Again, I know, let's say this is our VT vector here, and what I know is, let me use a different color, and this is it's quite difficult to plot it the same. So this is my current vector, okay, and that is cos, let me write it here, so cos theta is power factor, right? So then I add that one and that one, so again it's going to be like, if you just plot that one and that one, there will be 90 degrees, and that is J XS IA. So you are multiplying IA vector with J term, and you have that one, and that is what EF is. Okay, let me write here. So EF vector is equal VT vector plus J XS times IA vector, right? So let me use a different color, and I have that one, right? So I'm drawing exactly the same graph, and this is lambda and this is load angle. Okay, so my this part, let's discuss what happens. Okay, what happens if, I don't know, if current is increased with the same the same power factor, right? So instead of that, let me use a different color. Let's use the pink one, right? So now my current is increased, right? So that is my new current. Okay, so therefore, you know, the effect of that thing is going to increase, right? So now, anyway, let's use the green one. Okay, so that will increase my load angle, right? So this was the load angle. Let me use 1. So this is EF1, okay, and the red one, the green one is EF2. Okay, but I want you to see one thing here. So here, that is my load angle 2, right? So my current increased, and due to current increase, the voltage drop on that thing increased. So that means, okay, that means the load angle is increased. So you can say, again, we will prove those things. Torque is increased. Okay, so I am drawing like maybe more torque from that system. Actually, that is proportional, because again, there is no, you know, dissipative elements. And if I increase the current, again, I can write P out is equal 3, because of 3 phases, Vt times Ia times cos theta. I mean, in this case, voltage terminal is same. The current is increased, so output power is increased. So that output power has to come from somewhere, and your torque needs to be increased. And how can you increase? I mean, here it's not only the phase, but EF2 magnitude, okay, also larger than EF1 magnitude. So that means the field current should be increased. Okay, so let me put the case here, increasing current with same PF, right? Okay, cool. So let's move to a different example. And in this case, let's say you have, I mean, you don't have to draw a lagging power factor. Let's say you are drawing a unity power factor. Unity power factor. Okay, again, it is in the generating mode. Okay, so let's plot the graphs. Again, I'm not going to draw the circuit again. So we still have the same relation between EF and Vt. The only thing is our current will be in phase with Vt. Remember, the power factor is always defined between the current and voltage, the terminal voltage and the terminal current. It's not between EF. So EF, actually, there's not a point which you can connect your oscilloscope and measure EF. Okay, it's all the stator winding. So EF is a, you know, equivalent model that we invented to show the flux due to the rotor, but in reality, you know, all the electrical connections are made through here. You cannot connect anything to here physically, and you cannot measure that one just by connecting something. You need to calculate it. And, you know, again, power factor is always calculated at the terminus. Okay, so anyway, let me draw that one. Again, this is our Vt. Okay, and let's say this is our, use it straight. Come on, this is that, you cannot see that one on top of that one. Anyway, let me plot normally. So that is IA, right? Then you are multiplying it by j omega xs, okay, so j xs, so that is j xs ia vector, so it is 90 degrees, so I theta is equal to 0 unity power factor, right? So then you have, use that one, then that is your EF vector, right? So this is your load angle. Again, let's make it for, I don't know, leading power factor. It can be leading power factor as well. So let's try to draw that phasor diagram. So let's say this is VT, okay, and this is again, so this is IA vector, okay, and this is theta, so it is ahead of this is ahead of the terminal voltage, so that is the leading case, okay. For again I need to like multiply it by 90 degrees, it will be something like that. Again, if you can connect, so that will be 90, so that is j xs ia, right? Then that will be your straight line here, that will be your EF, okay, and that is your load angle, okay. So the important thing is, again, if you think of like these two phasors, okay, so if you move, okay, if you move that vector, actually for the lagging power factor, EF should be large, and actually for the leading power factor, so EF can become smaller, okay. So you can control, okay, again the magnitude, don't forget, so the magnitude EF can be controlled by the field current, okay. So by controlling how much EF is generated, again it doesn't have to be always from like that, actually you are controlling EF, okay, remember there is some IF here, so you are controlling EF and you have some terminal voltage here, and the current is not something you control directly. What you control is you control EF, and there's some voltage difference over some component here, then the current flows depending on the difference of these two voltage vectors, okay. So you shouldn't look like we decide current directly and then we see what EF is. It is usually the other way around. You choose some EF, the magnitude, and depending on the torque and the magnitude of the EF, then you end up having some currents, okay. So then let's look at the latest case where, I don't know, extreme case like 90 degrees leading power factor, okay. So 90 degrees leading power factor. Let's see what happens in this case, right? So again I am putting my VT here, okay. Then my current is 90 degrees, so in order to have 90 degrees EF, right, so this is IA, there's 90 degrees leading. So if you have that IA, okay, let me take myself here, if you have that's IA, and if you rotate 90 degrees you have something like that. Right. So, and your EA, again you cannot see the waveforms if I just draw the perfect lines, so let me use the other ones as well. So this is JXS IA, and then this is EF. Okay, and what is the load angle in this case? What is the load angle in this case? So EF and VT are totally coinciding. So if right here, so if theta is 90 degrees leading, then load angle is 0. So if there's no load angle is 0, so that means torque is equal to 0. I mean that is understandable, because if you somehow drove like 90 degrees leading current from here, even if you are drawing reactive power, the real power that you draw is 3 VTIA cos theta. Okay, so if theta is 90 degrees, there is no real power, and if there is no real power, there will be no torque. So that is, not surprising to have 0 load angle, and actually that is the magnitude of EF. That is what the EF should be. Let's look at the other case. Let's say 90 degrees lagging PF. Okay, power factor. So in this case it is more or less the same graph. So this is your VT, and this is your current, right? And it is 90 degrees here, IA, and if you rotate it 90 degrees, what you end up is the voltage, right? JXS IA vector, and then your EF again. So this is, it's really difficult to draw straight lines here. So this is EF vector. So here again load angle is 0. Okay, again in this one you have no torque in this case, but EF, as you can see, EF should be larger on the lagging power factor. With the leading power factor, actually you can control your field flux. So these are the different cases with this simple equivalent circuit in, let me write here as well, this is the generator mode, and I will solve some numeric examples as well, so don't worry, but it will be really helpful, at least if you can understand the phasor diagrams, how you can draw the phasors. Okay, but again we just talk about the simple model here, but the full model is like that. So this is the armature resistance, and this is armature reactance, or the total stator reactance. Let me write the stator reactance because there's also leakage. So this is the terminal voltage, this is current, phase current, so this is induced voltage, and then this is your field current. So again, we just, in the very simple model, we omitted the field current side, but normally you have some field resistance and there will be some losses on that part as well. And there is some field inductance, but usually that one is not really important because we are applying some DC field voltage. Okay, since we are applying some DC voltage under steady state conditions, that LF is not important. And again, what is important is EF is proportional with EF magnitude. Okay, so by controlling field current I can control the EF, and by changing the magnitude of EF you can control, if you can control that voltage here, even if that is connected to the grid voltage, so you don't have any control on the grid voltage on the right hand side, but if you can control here, you can control how much current is going to draw, or if it's not going to draw any current at all. So actually by changing the field current, okay, either you can make it very big to push the machine to the lagging power factor, or you can reduce it like really small, so you can push the machine come back to the leading power factor. So it is what you control here that is controlling EF, and the magnitude and the phase of that EF is determining how much current is going to flow through. So anyway, at the end of the day, this is not 100% accurate model. This is just a simplified model, but it makes us to model all that big generator when we would like to see how it behaves. So all that thing can be modeled like a simple circuit like that, and we can calculate all the power and torque relations. Okay, so this week also I will upload some numerical calculations using that equivalent circuit model. Thank you.